Okay, hello and welcome. Thank you for your interest in the Magic Open Data Analysis School. We had the idea, since the school is oriented towards newcomers, to provide on YouTube introductory videos, both to gamma ray astronomy in general and also to data analysis and statistics for gamma ray astronomy. You will find this in this very same YouTube channel of the Magic Collaboration by Giacomo. Okay, so my task is to introduce you to gamma ray astronomy. It's quite difficult, as you might imagine, to introduce someone to an entire field. So more than giving you a detailed introduction to all the aspects of the field, I really wanted to give you a broad overview, as broad as possible. So first of all, I wanted to give you the historical context in which gamma ray astronomy was born, because I would like you to be able to place gamma ray astronomy among the other branches of physics. Then I would like to present you the techniques and the instruments that are used for the gamma ray astronomy. So let's say the technology of gamma ray astronomy. And finally, I would like to discuss a bit the mechanism of gamma ray emission and the sources that emit gamma ray. So let's say the scientific part. So let's start with the context, origins of gamma ray astronomy. So at the end, sorry, of the 19th century, scientists already have discovered alpha, beta, and gamma radiation. This means they are aware that there is ionizing radiation. This can be either the nuclei of the helium particles, the electrons, or the gamma rays that ionizes the environment. In particular, they observe this through the discharge of electroscope. So then the next question is to determine whether this radiation is terrestrial or celestial in origin. And this is what Hess sets up to do with these balloon flights. The idea is basically to fly high and to measure the quantity of ionization as a function of the altitude. And what Hess finds out is that if you increase the altitude, the rate of ionization also increases. So this means that this ionization, this environmental ionization that we are measuring, is not of terrestrial origin, is of celestial origin. So this marks the discovery of cosmic rays. That means that has discovered that actually the Earth is constantly bombarded by charged particles that come from the universe. And basically, these charged particles produced from the universe are basically the beginning of particle physics, what I call under the sky particle physics, because all the particles that are discovered in the 30s and the 40s, the positron by Anderson, the muon by Anderson and Edermeyer, the charged pions by Lattes, all these particles are basically discovered by exposing a particle detector, can be a cloud chamber of a stack of nuclear emulsion, to the sky, then observing the results, the particles that have interacted in your detector. So really, the birth of astroparticle physics is the birth of also of the modern high energy physics, of particle physics as we intend it nowadays, that is searching for new particles, no? In the second half of the 30s, Auger makes a very important discovery that actually all this radiation this ionizing radiation that we are observing, all these particles that we are measuring are basically the secondary of a primary particle that has interacted somewhere in the atmosphere and that has generated an extensive air shower. So what is a particle shower? It's basically a primary particle, as you can see in the second image, that interacts and produces a cascade of other particles through strong or electromagnetic introductions. Okay, you can see here the phenomenon contained in a single detector. You have to imagine that this happens all the time in the atmosphere. There are particles, as you can see in the computer simulation, that interacts at orders of 10 kilometers, well, let's say pretty much everywhere in the atmosphere. Here the drawing shows the interaction at 20 kilometers, and then they produce this immense cascade of particles. As you can see from the size of the simulation, there is even a city at the bottom of the simulation to show that the huge scale of these events. How does Auger realizes that all the secondaries come from a single primary particle? What he does is he basically scatters several particle detectors and basically observe observes a coincidence signal. So there are events that trigger simultaneously arrays of particles scatters over areas of hundreds of square meters. Okay, so that's when they realize that really all the particles that we have seen so far, those that Hess measured, those that the early particle physicists measured, are just secondaries of this immense extensive shower. And then another important discovery that we will actually use to do gamma ray astronomy is the discovery that this extensive shower produce Cherenkov radiation. What is Cherenkov radiation? It is the electromagnetic equivalent of the sonic boom, basically. As you know, the speed of light in a medium is attenuated by a factor n, where n is the refractive index. So you can imagine that you have a particle that a relativistic particle that in a medium is moving almost at the speed of light, but the perturbation, the electromagnetic radiation that is producing by polarizing the particles around its trail, it's moving slower than the particle itself because the electromagnetic radiation is attenuated by the speed is attenuated by this factor n. So it's basically exactly as an airplane that moves faster than the perturbation that it produces in the air, basically. So you get the generation of this electromagnetic front. The light that is generated is a thin light that peaks, let's say, in the blue wavelength. And you can see here an example from a nuclear reactor. In this case, the reactor is also producing particles that are then producing Cherenkov radiation. Here, in this very nice simulation, we see at once the discovery of Auger and the discovery of Galbraith jelly, because as we will see, we have three types of particles. We have a gamma ray proton and a nucleo of carbon. And in red, we can see the particles produced in the shower by the interaction. And then we see also the thin blue light produced by the Cherenkov radiation, okay? One thing that we need to observe is that gamma ray shower are very compact. This will become useful later when we start to do gamma ray astronomy. You can see again the particles and the Cherenkov light that they produce. 55, the year after Galbraith and Jelly, 54, sorry, the year after Galbraith and Jelly discovered Cherenkov radiation, I think it can be classified as the year where the community splits in two, because basically that year at Berkeley, they put into operation the Pevatron. With the Pevatron, you can now accelerate protons up to GeV energy. So basically, you don't need anymore to leave your detectors down the sky to search for new particles. You can basically produce them in a laboratory. And basically, once you can accelerate particles to GeV energies, you really access a new range of physics because you can start to produce antiparticles, and indeed they discovered the antiproton at Pevatron, or you can start to smash nuclei, etc., 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 etc. Basically, what is born is what we nowadays call high energy physics. So we accelerate particles in a controlled environment, and we study the other particles that we produce or how these particles are constituted, let's say. On the other hand, we have people that keep investigating the nature, the astrophysical nature of particles. So they continue the work of Auger and others, of Hess, Auger and others. So in 54, we have the first measurement of the distribution of the cosmic ray energies. We will see that later in much more detail. And in 58, in this branch, in particle physics, we have the first speculation on astrophysical production of gamma ray emission, because the intuition is that, well, if we have clear by now that somehow the universe is producing, is accelerating charged particles at the highest energies, well, once these particles interact with their environment, they should produce radiation of the highest energies as well. This is basically the argument of this paper on gamma ray astronomy by Philip Morrison. And then in the 60s, gamma ray astronomy is actually born through the launch of Explorer 11. I would not use yet the term astronomy, though it is used in the paper that advertises the detection of 22 gamma rays, because we cannot yet pinpoint sources by this time. We just know that we detected 22 gamma rays with this instrument that clearly don't come from Earth, that either come from the atmosphere or from space, but really not yet pinpointing sources. So before actually entering the history of gamma ray astronomy, let's try to imagine and let's try to describe how gamma ray detector is actually built. I really liked the sentence that I find in a review, that is, the history of gamma ray astronomy is the history of gamma ray telescopes. So let's start to imagine we want to build a gamma ray detector. What should we take into account first? Well, first, we should take into account how gamma rays interact with matter, no? So we can go to the particle data group and go to the section particle photons interaction with matter, and we will see this type of plot, no? Of the cross-section that we can read as the probability of interaction as a function of the energy. What happens when we start to have MEV photons, what we normally address as gamma rays, what we really call gamma rays? That we have Compton interaction, right? So we can exploit this to have, let's say, what we could call Compton gamma ray astronomy. And then at the higher energies, let's say above tens or hundreds of MeV, we have pair production. So we have pair production gamma ray astronomy that will actually be the focus of this talk, let's say. And here on the right, you have the same plot, but on the y-axis, you have the atomic number of the absorber. Something else that we should take into account, yes, the environment. Luckily, from the point of view of life on Earth, the atmosphere is opaque to any radiation above the UV, well into X-rays, and above into gamma rays, as this plot shows. The atmosphere is basically opaque to radio and to optical photons, let's say, to optical light. And as I said, no, luckily for life on Earth. So this represents a difficulty for gamma ray astronomy, right? Because it means that we should have satellite to detect gamma rays. Or maybe going back with a second to the phenomenon of extensive air shower, maybe it's not necessary to go out into space to measure gamma rays, no? We will see later that. I'll describe very quickly Compton telescopes just for completeness. Basically, the idea is that in a detector, you capture the Compton effect. Basically, you have a photon, a gamma ray that enters, scatters an electron, and you can measure the recoiling electrons. And by doing so, it loses energy, no? So basically, then you can reconstruct the energy and the scattering angle. The problem is that you have ambiguity on the entering angle, let's say. So it becomes complicated to do astronomy because you cannot pinpoint the origin of the gamma rays unless you have many events. These were the first Compton telescopes, were the first type of gamma ray telescopes. They are typically balloon or satellite borne, and they are very small survey instruments. Let's really enter now into pair production gamma ray astronomy, into the gamma ray astronomy that we are interested in. So as we said, the atmosphere is opaque to gamma rays, no? So a first idea might be simply to load a detector on a satellite and to basically make pair production happen within your detector, no? Once pair production happen within your detector, you can reconstruct the properties of the incoming photons like direction and energy. This is what is called a pair conversion telescope. They typically orbit at around 500 kilometers above the surface of Earth, and they are very small instrument because, as you might imagine, it is expensive to put material into space. They work pretty well in the range that we define high energy, between 100 MeV and 100 GeV. We shall see that the flux of astrophysical sources is steeply decreasing with energy. So at a certain point, when you go above 100 GeV, the fluxes of the source is so weak that having a surface of 1 square meter doesn't really grant you a sufficient detection power. In that case, if we remember Auger and if we remember the experience of Galbraith and Jelly, what we can do is to basically use extensive air shower as a way to measure gamma rays. So we can basically incorporate the atmosphere in our detector. In the very same way that cosmic rays produce a cascade of particles, gamma rays do as well. But the cascade produced by gamma rays are mostly constituted of electrons, positrons, and other photons, other gamma rays. So it's typically what we call an electromagnetic cascade. So once we have the development of the extensive shower produced by a photon, we can choose either one to measure the charged component of of the shower. So this would be, let's say, the improved version, the extended version of the Auger experiment. We just set up an array of particle detectors and we measure the charge component. And through this, we reconstruct the initial gamma ray. Or since we now know that the shower produces also Cherenkov light, we can measure the Cherenkov light emitted, no? And this is what imaging Cherenkov telescopes do. You basically have a big reflector and a camera with fast electronic to capture the development of this very thin light. The shower maximum occurs at around 10 kilometers, so these instruments are typically placed at very high altitude, and the effective area are very big because basically you have an array of detectors scattered over several hundred square meters or even kilometers. And basically for the telescopes, you have very large reflecting surfaces, as we shall see. This range is called very high energy. So it's typically optimal for gamma rays above 100 GeV because they can produce basically air shower big enough to be detected. So a bit more technical details on pair conversion telescopes. They are basically constituted of a tracker and of a calorimeter. The tracker serves basically the purpose of converting the incoming gamma ray into two electrons that we can track, such that we can reconstruct the direction of the incoming photon. And then basically we have also a calorimeter to capture this electron and measure the energy, obtain an estimate of the energy of the incoming photon. In the first experiment, like IGRET, the tracker is a spark chamber. And in more modern instrument like Fermilat is basically interleaved layers of silicon tracker and heavy material like tungsten to make the pair conversion happen. Okay, then you have a calorimeter, sorry, that usually is scintillating material. Each time we want to measure gamma rays, basically we will be overwhelmed by cosmic ray air shower. Even for the most bright gamma ray sources, the flux of charged cosmic rays, of protons from cosmic rays, is 100 times or 1,000 times larger, right? So we have to find a way to suppress this background. Basically, we're not interested in cosmic rays, just in the gamma rays. This is done through an anti-coincidence detector. So there is another particle detector encasing the tracker, and this is basically Vito's charged particles. These instruments are very good since they are on orbit. They have a very big field of view, meaning the patch of sky that they can observe. And since they orbit, they can cover the entire sky in pretty much 2 hours. These are the numbers for Fermilat. The angular resolution is at the order of the degree, which is not very good when you consider much more precise instrument like at lower energies. But the duty cycle is 100%. Basically, they can work modulo, let's say, technical problems. They work all the time. And as we said, the limitation is the effective area. Cherenkov telescopes, we pretty much explain how they work. Basically, you have a very big reflecting surface. Typically, it's a mirror, composite mirror of 10 order of magnitude 10 meters in diameter. And then you have a camera with pixels that are photomultiplier with very fast electronics because the flashes of Cherenkov light are really fast, of the order of nanoseconds. So through this technology, you can capture basically the development of the shower. The disadvantage of this instrument, they are ground-based, of course, they are not in space, is that the field of view is very small because they are pointing instruments. Since they are on the ground, you can observe a small patch of the sky and you have to point them. Their angular resolution is very good. It goes well below 1 degree. Also, their energy resolution and their effective area is quite big. So they are efficient in detecting very faint gamma ray emission at the highest energy. Unfortunately, they can only work at nighttime because the Cherenkov light is very dim. So you need dark conditions to observe it. And also you are subject to atmospheric condition. You really want to have a good atmospheric condition to make this type of observation. So the duty cycle is something around 10 to 15%. Also, moon can be a problem because a very intense moon can also affect your capacity to detect Cherenkov light. When you have more than one instrument, then you can apply the stereoscopic technique. It means you can, let's say, reconstruct more accurately the position of the incoming gamma ray, because now you have basically a measurement of the development of the shower from different perspectives, from different telescopes. And finally, so we cannot encase our telescopes in some anti-coincidence detector. So how do we reject cosmic rays that, as I said, are anyhow drowning the gamma ray signal? Basically through the topology of events. If you remember, when we observed the computer simulation of the shower with the Cherenkov emission, I remarked that the electromagnetic shower was very narrow, very compact. This results in the fact that its Cherenkov image, the Cherenkov light that produces, is also will result in a very compact image in the camera, usually something like an ellipse. Hadronic showers have large transverse momentum due to hadronic interactions. This means that they have very scattered and large imprint, and the same will be true for their Cherenkov light. So typically it's possible to disentangle between the two images, because the one produced from gamma rays will be, as you can see from the top image, very compact in your camera. Particle samplers are basically, as we said, their objective is to measure the charged component of the shower. You can do that either with scintillators, you can do it with tanks containing water with a photomultiplier, such that you see the Cherenkov effect of the particle in your detector, not in the sky. Let's not be confused by this, okay? We measure the charged particles. They are ground-based, but since they occupy a very large area and they are not pointed, they can observe a very large fraction of the sky. The angular and energy resolution, though, is a bit worse compared to ESCT, but they have also very large effective area and very large duty cycle. Since you are not observing the Cherenkov light of the shower, you can operate during the whole day. It doesn't affect your capacity to detect charged particles. And then they can explore what we call the ultra high energy regime, because they have very big collection area, so they can even measure fluxes above 100 TeV. And same as for a Cherenkov telescope, the discrimination between gamma and hadrons is done through the topology of events. This is the Hawk telescope that uses water tanks to detect the charged particles. And as you can see, the signature of a gamma ray shower is always very compact, while the signature of a cosmic ray shower will be always more scattered. Okay, so again, gamma hadron separation through events topology. So we got more or less the different types of technology that can be used to build gamma ray instrument. So this scheme is basically an overview of their development. Have the energy range on the y-axis and the time on the x-axis. So basically, in the 80s, we had only one instrument that was called COSB. There was another NASA instrument, SAS-2, that detected a few gamma ray sources, but COSB was really the first instrument to detect galactic and extragalactic gamma ray sources. Although very few, as we shall see in a moment. Then the 90s were the time of the Compton Gamma Ray Observatory. That was an orbiting instrument that contained both a Compton Gamma Ray Telescope, COMTEL, and another per-production telescope, the IGRET. It operated for 10 years and discovered a lot of sources. This was the period in which as well the first and second generation of imaging atmospheric Cherenkov telescopes were developed. In particular, in 1889, the Whipple telescope, that at the time was already being built for a couple of decades, detected firmly signal from the Crab Nebula at very high energies. In the following decades, CGRO was decommissioned, and basically scientists started to build the third generation of imaging atmospheric Cherenkov telescopes like MAGIC, whose data we will use in the tutorials, HESS and Veritas. Then we had the first construction of particle samplers like Milagro, that is now decommissioned, and Hawk, that is still operating, as well as the third generation of Cherenkov telescopes. They are still operating. And I think a revolutionary instrument in the field was the pair conversion telescope Fermi-LAT that is still in operations in 2008 and as we shall see in a moment, detected thousands of gamma ray sources. So this is what is represented in this plot. It's called the Kifune plot. It basically shows the number of sources detected as a function of time, basically. In blue, we have high energy per conversion telescopes. And in red, we have both Cherenkov telescopes and particle samplers. And as you can see, by this time, with the catalogs of Fermi-LAT, we have achieved a number of 5,000 detections. This is very low if you compare to the number of sources in an optical catalog, but still it's very big for the field. And what I would like to highlight is the evolution of how we see the gamma ray sky. We go from the sky map, basically of COSB, in which we see just as dots, the few sources that were detected, and in white you see the area that was scanned by the satellite. And then in the bottom plot, we see the old sky map of Egret above 100 MeV. Here, instead of pinpointing the individual sources, we have basically a histogram of the gamma rays detected. We can clearly see in this projection the galactic plane and the individual sources. And then we can see how the same basically plot is produced with data from Fermi for 12 years of observation from Fermi-LAT satellites. You really see how the resolution of the gamma ray instruments improve and the huge number of sources that now populate the gamma ray sky. Okay, so due to their technical nature, due also to the fluxes that very high energy instrument measure, we didn't detect as far as many sources as Fermi-LAT. We are stuck around 200, 300, 200 sources, let's say. But this will change with the next generation of very high energy gamma ray instrument. I will briefly mention them. I will not enter into technical detail. The Cherenkov Telescope Array Observatory will be the first Cherenkov Telescope Array to have two sides, one in the north and one in the south, in order to achieve full sky coverage, and basically is built as an array of different Cherenkov telescope, each one suited, as you can see from the plot, to be optimal at detecting sources in different energy ranges. And you can see here the three types of telescope: large sized, medium size, and small size, and how they will be most performant in different energy bands. As you can see from these sensitivity plots, which basically illustrates the minimum flux that you can detect with a certain significance, you would really have an order of magnitude improvement with respect to current instruments like Magic, Veritas, and HESS. Another very important instrument is the Large High Altitude Earth Shower Observatory, LASO, that is built in the Sichuan province in China. And basically, it's, if you want, an improved version of observatory like Hawk, because it has simultaneously water tanks in the center, and then you have basically an area of 1 kilometer squared cover of scintillators and water bugs to detect both electrons and muons. So yeah, this instrument, it's really starting to explore gamma ray astronomy well beyond 100 TeV and has produced already important results at 1 PeV. And as you can see from the sensitivity curves of the water Cherenkov detector array and of the kilometer square array, it will nicely complement CTA at the highest energies. Okay, so let's go, before going in the last part, let's try to make a quick mental recap of what we saw until now. So we saw that gamma ray is a discipline that is simultaneously a branch of particle physics, of astroparticle physics specifically, and of astronomy, of traditional astronomy, because it's an extension to the higher energies of astronomy that we commonly practice at lower bands. Then what we saw is that it has, since it has this connection to particle physics, it has this strong connection with investigating the process of acceleration in the universe. Basically, no? It was born out of astroparticle physics, no? That was studying how the universe accelerates cosmic ray particles. finally, we investigated a bit the technology, and we saw that, well, we are more interested in, we can either detect gamma rays via the Compton or the per-production effect, but we will be more interested in per-production instruments, and we saw that we can either have telescopes in the per-conversion telescopes in the high energy regime, spaceborne, or we can have ground-based Cherenkov telescopes and particle samplers that use the phenomenon that we discussed of the extensive air shower. So let's go now in the mechanism of gamma ray emission. How are gamma ray emitted, and which sources do emit gamma rays? So first of all, as we said, we have this strong connection with particle physics and with investigating the origin of the particles accelerated in the cosmos. If we were, how are basically carry on the legacy of Auger, Rossi, Hess, and all these people? Well, nowadays we can measure, thanks to instrument like Auger, that was titled after named after the scientist. We have basically particles arrays scattered over enormous area. You can see here a square of 70 kilometer size. And through them, we have achieved a very good precision in measuring cosmic rays. So you remember that I said that Rossi was the first one to measure the cosmic ray spectrum. Well, now we can measure the spectrum, that is the distribution of energy of the cosmic rays over 12 decades in energy, right? We have the capabilities to measure with different instruments, as you can see in the plot, on the plot in the right, the spectrum of cosmic rays. In particular, what you can see is, depending on the instrument, we are even able to discriminate between different particles that constitute the cosmic ray spectrum. So if we consider just the low energy band, let's say before 10 to the 5, 10 to the 6 GeV, as you can see, we can resolve the composition of the cosmic ray. So we can see that it's predominantly protons, and then we actually have helium as well, but we also have, beside heavier elements, we also have particles like electrons and positrons and even antiprotons. And then at high energies, due to limitations in the technique, we will not enter into the detail, you just have a cumulative cosmic ray spectrum. So cosmic ray spectrum from all the particles, let's say all the charged particles. The really striking feature of the cosmic ray spectrum is that it's basically a power law in energy. So the flux is really described by a power law in energy. The index of the power law is changing, but overall, let's say we can describe it with this power law. And if you're interested, this is a natural result of the acceleration mechanism that we nowadays call Fermi acceleration mechanism, and that was proposed by Enrico Fermi. What is really important, if you remember the split between high energy particle physics and astroparticle physics, as I said, the advantage of a detector is that you can really perform your particle physics experiment under controlled condition, but you are always limited in energy because the energies that the cosmos is producing are orders of magnitude bigger, larger, as you can see, than the one that you can produce even at the most modern accelerator like LHC, okay? So we know for a fact that astrophysical sources are accelerating particles to relativistic energies, right? Somewhere within these astrophysical sources, particles are produced in this power law-like spectrum. But the issue is that both in the environment around the sources and both in space, there are magnetic fields that basically change the trajectory of this particle. No, as you know, a charged particle will start to spiral in a magnetic field. So the problem is that even if we can detect the cosmic rays from the universe at large, from all the sources in the universe, we cannot pinpoint which sources are producing cosmic rays, right? Because the protons will have these these helical trajectories, no? But on the other hand, the environment that is, let's say, distorting this trajectory, it's rich in many materials that can be protons, nuclei, photons, or magnetic fields, no? And as we know, when charged particles, I just put P as protons for an example, when charged particles interact with this environment, they produce high energy radiation, right? So gamma ray astronomy, gamma ray in this sense, the detection of gamma rays really brings about the possibility to do astronomy, right? Because we can trace back to the sources, right? We can trace these high energy photons produced by protons back to their sources, no? So the idea is that basically we observe a source in gamma rays, we analyze the data, and through some inference, which involves some assumption on the environment that produced these gamma rays, we can basically go back to the particle spectrum produced in that source. Okay, so that is really the relevance of gamma ray astronomy. It is astronomy per se because you can pinpoint sources that are producing these very high energetic photons, but more than that, once you detect these photons, you can really do particle physics. Basically, you can infer the mechanism that have accelerated this particle. You can study the acceleration process. What type of spectrum would a source that produces cosmic rays have? Let's start from a source that does not accelerate charged particles to the highest energies. Let's consider a normal galaxy, a spiral galaxy like the one that we live in. We will call it inactive for the time being. So what radiation does this galaxy produce? Well, basically it produces the thermal radiation of all the stars that are within this galaxy, right? So if we want, we could very roughly, neglecting other physical process, model the emission as basically the sum of the radiation of main sequence star, basically. So 10 times, 10 to the 11 times the suns that are in this galaxy, right? And we will not be so wrong, let's say. As you know, the stars are producing black body spectrum. No? They are a system in thermodynamic equilibrium. Well, when we observe a source that is indeed accelerating cosmic rays, this is the case of this active galaxy, active because it has basically a black hole in the center that is launching these two jets of plasma where particles are accelerated. Okay, so much different than the outlook of the normal galaxy. Okay, here there are high energy physics processes at play, and in this case the radiation of this type of galaxy, as you can see, it spans the entire electromagnetic spectrum. This is not equilibrium radiation, right? This is not radiation of the individual stars that are in thermodynamic equilibrium. These are the results of the interaction of the particles with their environment. And if we take a look at it in this differential spectrum in this differential flux representation, that is flux per unit energy, we can see basically a power law spectrum over several orders of magnitude in energy. Does it remind you of something? Of course, the cosmic ray spectrum, right? So yet another connection between gamma ray astronomy and astroparticle physics. Power law of photons can only be produced by the radiation of power law of relativistic particles. Okay, so studying the spectrum of gamma ray sources of non-thermal emitters in general becomes a way to infer the particle spectrum that is being produced by these sources, okay? So basically we can say that we can study astrophysical acceleration either directly via cosmic rays, but we lose any directional capability, or indirectly through gamma rays, but we acquire astronomical capability. No, we can pinpoint back to the sources. So, and as I explained before, non-thermal emission can be used to infer the acceleration mechanism. Again, I want to remark that the black spectrum is not the result of the red spectrum, because the red spectrum is the global deflux of charged particles from all the sources in the universe. We cannot distinguish the direction. But since summing up all the sources in the universe gives a power law, we have the understanding that in each individual source, there has to be some acceleration mechanism that produce a power law-like of particle, no? And that's what we aim to infer by studying gamma ray sources. So in this case, in the source marked Ariane 421, there has to be a power law of charged particles produced somewhere that is responsible for the gamma ray emission. Gamma ray emission processes, which are the way in which we can produce gamma rays, it's non-thermal processes. So if you have a population of particles at thermal equilibrium, you will not produce gamma rays. We can have either nuclear processes, that is the excitation of an atom, or the annihilation of a particle with an antiparticle. And these are non-thermal, definitely processes, but they're really related more to the environment around the sources than to the acceleration mechanism itself. but continuum emission processes like electromagnetic processes like bremsstrahlung, synchrotron radiation, inverse Compton, and also strong interaction like a proton-proton interaction or proton-gamma interaction. They're really related to the accelerated particles because here the subject, let's say, of the interaction, the particle that is radiating, is really the cosmic ray particle that we are interested to study, either the electrons and positrons or the protons. And thus, this type of thermal and non-thermal radiation really trace particle acceleration and even plasma dynamics. So it traces not only the sites where particles are accelerated, but even it traces the plasma, which are the region in which these particles are being accelerated as they move. You can see here astrophysical plasma basically imaged through its synchrotron radiation. In this case, we have the jets of a galaxy, and I think it's exactly the same galaxy that I showed you here in the exemplary figure. It's not the same galaxy. This is not Markarian 421. It's not the galaxy producing this spectrum. This is Centaurus A. And this is the explosion of a supernova, the remnant of the explosion of a supernova, where we can see as well particles radiating basically synchrotron radiation as they move through the shell of the explosion. Okay, so we can distinguish the radiative processes in leptonic and neutronic. Leptonic are the processes that involve leptons, electrons in most cases. We have synchrotron radiation. We can see here the jet of plasma of M87 through its optical synchrotron radiation. And this is the radiation, as you very well know, that you have when a particle is spiraling through a magnetic field. We can have bremsstrahlung, which is when a particle is breaking through the Coulomb field of another charged particles. This produces basically radiation in the X-ray regime. And then we have the inverse Compton, in which basically a high energy electron upscatters a soft photon to X-ray or gamma ray energies. And I just put some example of astrophysical sources probably radiating with these processes. So we already discussed M87. You see here a shell of a supernova remnant, IC443, and in a small place of the shell, you can see this possibly this Bremsstrahlung emission in X-ray. And here you can see the very impressive image of gamma rays in the jets of this binary system. We will quickly see, we will quickly present these objects later. Keep in mind that if you have leptons, electrons radiating via synchrotron or Bremsstrahlung, this emission will mostly appear in radio to X energies. So if you have leptons radiating gamma rays, it's most probably via inverse Compton. We can have strong interaction as well, and this is the case in which photons interact with matter or with photon fields. And in this case, the electromagnetic emission is seen in gamma rays, no? Because you have basically a proton that collides with another proton, produces a pi 0 and two photons, or a proton that interacts with a gamma and produces pions, among which pi 0 that decay in gamma rays, no? So really the image that we see for certain sources, if we assume that they are radiating via proton interaction, is really the the protons interacting with in gamma rays. We really have an image of the protons interacting with their field, let's say. Okay. Normally, we have this representation of the differential flux as a spectrum energy distribution. It's basically obtained by multiplying by E squared the flux, the differential flux on the source. And in this case, the units are basically power per square centimeter. And what is really interesting when you do this type of representation is that when you switch to the spectral energy distribution, what you are seeing is basically the power emitted across the electromagnetic spectrum. And as you can see, for sources that emit up to gamma rays, even if the flux is really low, given the energy that each photon carries, the power that they release in gamma rays is almost comparable to the power that they release in other wavelength, right? So astrophysical accelerator release roughly half of their power in gamma rays, half of their electromagnetic energy in gamma rays. And this, I wanted you to memorize this double bump structure because with a gamma ray peak separated from the peak at the other wavelength, because it's really common among different sources. So we have here active galaxy, Markarian 421, and here you see that the gamma ray peak is separated from the other peak, and basically it's due to inverse Compton in one of these possible interpretation. And it's the same for other sources like the supernova remnant, where you see that the gamma ray peak is separated from the other continuum radiation, that is synchrotron, as for the active galaxy case, and in this case the high energy radiation is attributed to the pi zero decay, so to proton-proton interaction. I really wanted you to keep in memory this double bump structure. Okay, so let's conclude with a quick overview of the sources that emit gamma rays. We know how the gamma rays are emitted by now, either leptonic or hadronic processes. What type of sources do we have that produce gamma rays? For convenience, we usually classify them in galactic and extragalactic, no? Sources that are in the galactic plane, possibly in our galaxy, and sources that are far away from the galactic plane and most probably outside of our galaxy. So how are galactic sources in general? In general, this is not an absolute characterization. This is some common feature that if I were asked, I would extract from galactic sources. They have mildly or non-relativistic outflows of plasma, so they have jets or a remnant of a supernova explosion, and they are moving at a not significant fraction of the speed of light, okay? And they span, they are not so big, they typically span tens of parsecs. So plasma moving at a fraction of a speed of light along, let's say, tens of parsecs, okay? And here you have interaction either with the environment or with the photon fields produced by the charged particles themselves. This is the case of supernova remnant and binary sources. Supernova remnant we already discussed when we actually looked at the image of this source, RxJ1713. Basically, in this type of sources, you have acceleration within the ejecta of the supernova, and then you have interaction of the protons with the surrounding material that produces this pi zero bump, this pi zero gamma ray spectrum. Or you can have in objects like binaries that are basically a system of two co-orbiting stars. It can be different type of stars in different states of their life, but basically it's a star that is accelerating particle either through the ejecta or through a jet. And then this particle's acceleration is interacting with a photon field produced by a companion star or from the particle themselves. And you can see here the RS-Ophiuchi nova, in which basically you have acceleration of particle in ejecta that are interacting with the protons around the source. Okay. And the other source illustrated here is what we call a microquasar. It's actually this source S433. It's basically uh, uh, a dead star that is eating the material of a companion star and spinning it up to create two jets. Okay. Another important source that we'll actually find in our MAGIC dataset are pulsar and pulsar wind nebula. This is in a sense a very similar object because it is a dead star, a neutron star within the shell of let's say the shell of its previous self, let's say the exploded shell of the supernova. So inside you have a neutron star that is spinning very rapidly, and we will see how we can determine with gamma rays the signal of the spinning star. You have particle acceleration in the regions in the magnetic field basically generated around this star, and pulse emission. And basically this pulsar is driving some winds, some clouds of some basically winds of accelerated particles that are interacting with the clouds of magnetized plasma around the source. The difference between the two is that the pulsar in the center has very steady emission. This is an image in the X-ray, and this is a combined image. And the source outside has very steady emission. And we will actually use these type of sources. We will construct the phaseogram, that is the histogram of the phases of a pulsar, not of the Crab pulsar, but of Geminga in our dataset. And then we will also study the Crab nebula, that is a very steady and bright gamma ray emitter. Extragalactic gamma ray sources are much bigger than the galactic ones. They are typically, they have the size of the galaxy. Some source, like AGN with jets, basically are launching plasma to sizes that are much bigger than the entire galaxies hosting the active nucleus. You can see here basically that the jets of Cygnus A are much bigger than the galaxy hosting the black hole that is uh, launching them. And these are very fast. Even though this is an immense amount of material, this plasma is traveling as at significant at velocities that are a significant fraction of the speed of light. So in this case, we have highly relativistic and collimated plasma outflows, differently than for the galactic sources, what we had basically non-relativistic and non-collimated outflows. And then we don't have much matter around here. We mostly have photon fields, which is radiation from the galaxy or the jet itself. So mostly we have interactions of electrons and protons with surrounding photon fields. Okay, so the other thing is that since they are traveling so fast, the radiation is Doppler boosted. So for active galaxies with jets that are collimated relativistic outflows of plasma from kiloparsec to megaparsec scale, they are actually most of the sources that we observe in the gamma ray sky, because basically if the jet is pointing at a small angle with respect to you, we call this type of source blazar, then basically you really see a strong Doppler boosting of the radiation. This means that they will appear more frequently in catalogs, no? Because these are the brightest sources due to this relativistic Doppler boosting of the radiation, to their relativistic motion, they will be the brightest sources. The high energy emission is either interpreted as due to inverse Compton of the synchrotron photons of the jet, sometimes or of other photon fields around the source, or sometimes in some models also let's say explained as the result of the interaction of protons, high energy protons, with the photon fields. Okay, and the emission is highly variable in different bands. You can see here the Markarian 421. Actually, we will reproduce this light curve at very high energy, and as you can see, the flux as a function of time is very variable in all the band in which we can measure it: radio, optical, X-rays, and very high energy gamma rays. Okay, so very bright, very strong, very variable sources. Another source worth mentioning are GRP. We have short or long GRP according to the duration of this phenomenon, which is basically the explosion of some system involving black hole. It can be the coalescence of two black holes, or it can be basically the explosion of a nova. When you have this phenomenon, probably you have some kind of jet formation or some, let's say, strong collimated outflow of plasma that produce radiation in different bands. They are continuously detected by a spaceborne telescope, especially in X-rays. They are typically 90 per year in hard X-rays and 240 per year in MEV gamma rays, but they are not so much detected at higher energies, because as you can see from the plot on the right, you have a very erratic phase of emission, very strong and erratic phase of emission that we call prompt emission in X and gamma rays, and then you have a steeply declining flux as a function of energy. Nonetheless, we had very significant discoveries in the last decade, basically, because in 2017 we detected the first GRP in coincidence with a gravitational wave, so the merging of two neutron stars. And then as well, we started to detect the brightest GRP at very high energy. So for the first time, we started to detect basically GRP, even though, as you can see, the flux is steeply declining in gamma rays. We have now the sensitivities and also the observational program apt to detect this type of sources. And we had detection of very high energies both by Cherenkov telescopes and actually by a particle sampler that recently detected the brightest GRB of all time. And I think that's it. That's the end of our tour of gamma ray emitters. So again, let's make a quick recap before closing the video. I want you to keep in mind the strong connection between gamma rays and cosmic rays. Gamma rays are not only a mean to do astronomy, but represent a strong connection to the acceleration mechanism. We saw that we have basically different type of radiation produced by discharged particle by the cosmic ray that result in gamma rays. Most probably, let's say, interaction of the high energy particles either with their environment or with photon fields. This is what we see in almost all astrophysical sources. Doesn't matter if they are galactic or extragalactic. And as we saw, very importantly, almost half of the energy of the power of these sources is released in gamma rays. So this concludes my introduction. I really hope it was useful and it was interesting, and you are invited to, I invite you to read more books or reviews if you want really to dig deeper in the topic. Thanks a lot for your attention.